Section 7.3 of your textbook covers the elimination method for solving systems of equations. Remember that a system of equations is a set of two or more equations that are to be solved simultaneously. A solution of the system must also be a solution of every individual equation in the system. Previously, we've studied the graphing method and the substitution method for solving systems. And like the substitution method, the elimination method is an algebraic method. It's also sometimes called the linear combination method, and it's a particularly useful method in the branch of mathematics called linear algebra, which often deals with solving systems of three or more linear equations. In this class, however, we will continue to focus primarily on systems of two linear equations. So to use the elimination method to solve a system, first we will rewrite both equations in the form ax plus by equals c. Second, if necessary, multiply one or both equations by a constant so that terms containing the same variable have opposite coefficients. Third, add the two equations to eliminate one variable. Next, solve the resulting equation to find the value of one variable. And finally, substitute to find the value of the other variable. Let's look at an example. In our system, 2x minus 3y equals 17 will be equation 1, and 4x plus 3y equals 7, we'll call that equation 2 for easy reference. Notice that both equations are already in the form ax plus by equals c, and also notice that the coefficients of the y terms are opposites. First equation has negative 3y, the second equation has positive 3y. So we'll move right to step 3 of our process, and we'll add the two equations together in order to eliminate the variable y. On the left-hand side, combining like terms, we obtain 6x, and the y terms cancel out. On the right-hand side, 17 plus 7 is 24. Notice that as we do this step, we are actually using the addition property of equality. Equation 2 tells us that the expression 4x plus 3y is equivalent to the number 7. So we can add 4x plus 3y to the left-hand side of equation 1, while adding 7 to the right-hand side of equation 1. And that's how we obtain the equation 6x equals 24. Now we can solve for x by dividing by 6 on both sides to find that x equals 4. In order to find y, we may substitute back into either of our two original equations. Let's use equation 2. So 4 times 4 plus 3y equals 7. Or 16 plus 3y equals 7. Isolating the variable, subtract 16 on both sides. 3y equals negative 9. And then divide by 3 on both sides. So y equals negative 3. This means that our solution set for our system contains one point, which is the point 4, negative 3. If we were to draw a graph of these two linear equations, we would see that they intersect at the point 4, negative 3. Let's look at some more examples, gradually increasing in complexity. Number 1, 3x minus 5y equals 16. That will be equation number 1. And 6x plus 2y equals 8. We'll call that equation 2. Both equations are in the form ax plus by equals c. However, neither the x terms nor the y terms have opposite coefficients. So we will need to multiply one or both equations by a constant. In this case, the simplest way to obtain opposite coefficients would be to multiply equation 1 by negative 2. And if we multiply by negative 2 on both sides, we obtain a new version of equation 1, negative 6x plus 10y equals negative 32. Notice that as we compare to equation 2, we now have opposite coefficients for our x terms of our two equations. And we can now apply the elimination method by adding both equations to eliminate the variable x. So our new equation is 12y equals negative 24. Solving for y, we obtain y equals negative 2. We can now substitute back into either of our original two equations in order to find x. Let's use equation 1 this time. 3x minus 5 times negative 2 equals 16. Or 3x plus 10 equals 16. We can isolate our variable by subtracting 10 on both sides and then dividing by 3 on both sides to obtain x equals 2. This means that once again, our solution set will contain one point, the point 2, negative 2. Moving on to example 2. Equation 1 is 2x plus 3y equals 13. Equation 2 is 5x plus 4y equals 15. In this case, multiplying one of the equations by a constant will not be enough in order to obtain opposite coefficients for either the x terms or the y terms. So we'll multiply both equations by constants. Let's multiply equation 1 by negative 4 on both sides. And let's multiply equation 2 by 3 on both sides. Notice that when we do this, we'll obtain a y term of negative 12y for equation 1 and a y term of positive 12y for equation 2. Let's rewrite our equations. Equation 1 now says negative 8x minus 12y equals negative 52. And equation 2 now says 15x plus 12y equals 45. So if we add these two equations together, we will eliminate the y terms and obtain 7x equals negative 7. Therefore, x equals negative 1, and we can substitute back into one of our original equations to find y. Let's use equation 1. 2 times negative 1 plus 3y equals 13. Negative 2 plus 3y equals 13. Adding 2 on both sides, 3y equals 15, and dividing by 3 on both sides, y equals 5. So the solution set, again, contains one point. In this case, the point negative 1, 5. Before we move on to our last two examples, I want to note that we had another option when solving this system. Instead of multiplying by constants to eliminate the y terms from our equations, we could have multiplied by constants that would enable us to eliminate the x terms. For example, if we multiply the first equation by negative 5 on both sides, we would obtain negative 10x. And if we had multiplied the second equation by 2 on both sides, we would obtain positive 10x. Then we could eliminate the x terms and proceed to solve the system. Up to this point, we have seen three systems, all of which had a solution set that contained one point, which means that they represented intersecting lines. However, we know that there are two other possibilities for solving systems of two linear equations. We could obtain a system that represents parallel lines, in which case there would be no solution, or we could obtain a system of two equivalent equations, in which case there would be an infinite number of solutions. All of the points that satisfy the equations would be solutions. So let's look at two more examples to see how the elimination method would lead us to those kinds of conclusions. In example number 3, 2y minus 4 equals negative 3x, we'll call that equation 1. And 6x plus 4y equals 8, we'll call that equation 2. We'll need to rewrite equation 1 so that it's in the form ax plus by equals c. Let's add 3x on both sides and also add 4 on both sides so that equation 1 now looks like this. 3x plus 2y equals 4. Now if we compare equation 1 and equation 2, we notice that there are no opposite coefficients for our x terms or for our y terms. So let's multiply equation 1 by a constant on both sides. If we multiply by negative 2, we can obtain the opposite coefficients we're looking for. So equation 1 now says negative 6x minus 4y equals negative 8. And equation 2, we'll recopy that underneath, is still 6x plus 4y equals 8. Now if we add these two equations together, notice that both the x coefficients and the y coefficients are opposites. So both variables will be eliminated, and the left-hand side of our equation just is 0. On the right-hand side, negative 8 plus 8 is also 0. So we've obtained an equation that is always true. What this means is we have an infinite solution set. These two equations are equivalent. Therefore, we will write our solution set using set builder notation. Let's go back to the original version of equation 1 and isolate y. If we add 4 to both sides of our original version of equation 1, we have 2y equals negative 3x plus 4. And if we divide by 2 on each term, we obtain y equals negative 3 halves x plus 2. Now we can write our solution set. It's the set of all coordinate points x, y, such that y equals negative 3 halves x plus 2. One final example, example number 4, 6y equals 4x minus 9. That will be equation 1. And 1/2 x minus 3/4 y equals 1. Let's call that equation 2. Our work will be simplified a bit if we clear the fractions from equation 2. So let's multiply both sides of the equation by the least common denominator, which in this case is 4. So equation 2 now says 2x minus 3y equals 4. Comparing that with equation 1, we note that equation 1 is not in the form ax plus by equals c, so let's rewrite it by subtracting 4x on both sides. To obtain negative 4x plus 6y equals negative 9. Once again, neither pair of variables has opposite coefficients, but we can obtain opposite coefficients by multiplying equation 2 by negative 2 on both sides. If we do so, our new version of equation 2 will say, actually let's multiply by positive 2, in order to obtain positive 4x minus 6y equals 8 for equation 2. Now we do have opposite coefficients for our x's, negative 4 and positive 4. For our y's, positive 6 and negative 6. So once again, when we add on the left-hand side, we obtain 0. And on the right-hand side, however, we obtain negative 1. This is an equation that is false. It's a contradiction. What this means is that our system is inconsistent, and the solution set is the empty set. If we were to graph these two linear equations, we would obtain parallel lines, which means that there are no solutions. And our solution set, once again, is the empty set.